lesson 8 of your differentiation chapter, and the topic today is parametric differentiation. So this is quite a nice little topic. Once you've done parametrics, there isn't much more to it. It's just that we needed to have covered the chain rule and the product rule to really be able to do the A-level standard questions on parametrics. So that's why we've waited for this topic until now. So nothing that you're going to be asked in terms of your specification is too complicated. You're doing first derivatives and you might be asked to find equations of tangents and normals. So let's have a look at it. So first of all, you need to remind yourself how parametrics work. So there's a review task for you, and your task is you've got the picture of the graphs. You're not to use your calculator, and you have to try and place your graphs in the right place in the table. So what I'd like you to do in a second is pause. The next slide that I'm going to show is some hints. If you get stuck, you can move the video on a little bit, and then the next slide is going to be the answers. So pause now and have a go at the task. Okay, and then here are some hints. You can look at the curves and have a think about what the parametrics might be. There might be some that you recognize. I would say there are some that you should be slightly familiar with, but you could also have a look at the table and just be having a think about if you're changing t, get some values of x and get some values of y and see what's happening there. Okay, so next slide is going to be the answers coming up. Right, so here's the answers. So one thing I think's worth pointing out is, for example, here you've got this column, x and t are related in a linear way. So the graphs for the Cartesian curve is almost what you would expect, because if you substitute here instead of t, if you had x over 2, y equals 2 sine x over 2, it looks like the shape of y equals sine, right? So I think there are things that you can have a think about. Anyway, those are those answers. Okay, so hopefully now you've reminded yourself on what parametrics are. The one that I thought you should be familiar with definitely was this one that relates cos of t and sine of t, and it comes out as an ellipse. Okay, so next we're going to look at the procedure for differentiating parametric equations. So I'll show you this example, and then we will take some notes as well on the the step by step. So have a look at this, and then we'll fill in your slide that you've got on the next page. Okay, so you've got x defined in terms of t, and so we can't do anything with y directly, but we can find dx by dt. Similarly, we've got y defined in terms of t, and so we can find dy by dt. And at this stage, you should be thinking, I bet I know what's going to happen. There's going to be a bit of chain rule action. You're right. I hope that's what you were thinking. You can write dy by dx as dy by dt divided by dx by dt. And the dt bit cancels out, and you can connect dy and dx directly. So what ends up happening, you differentiate x in terms of t, y in terms of t, you put the y bit on the top of your fraction, and you put the x bit on the bottom of your fraction. So that's what the procedure looks like. I hope that you have this slide and you can fill it in bit by bit. So what was dx by dt? What was dy by dt? What did we do to combine the two of them? And we were using the chain rule. That's how we applied the chain rule. I actually went in directly rather than using them multiplying, but this you can see exactly how the dt's have cancelled, and we have to flip up the second one to get dx by dt, and we're dividing by dx by dt. Because of that, we have to have dx by dt not equal to 0, and therefore what is dy by dx equal to, and it equaled the fraction that you saw on the working out on the other slide. Okay? Now, what I'd like you to do is have a look at this question, and I'd like you to pause the video and have a go see if you can find this gradient. Okay, hopefully you got it. I think it's fairly straightforward. So you get this fraction in terms of t, and then you're told t equals 2, plug it in, and you get a value for dy by dx, and that's you finding the gradient there. Okay, so what you've got now, this is part one. There is another video to watch, but before you do, I'd like you to do these practice questions. Find dy by dx, bit of practice of the differentiation you've been doing as well. There's this application where you need to do quite a few different steps. Just follow through. And then practice questions 2. So you're determining the coordinates of the stationary points of each of the following functions with exact answers. Now I'm going to show you the working for part A because this isn't that straightforward. So I'll just make sure that you sort of know how you're going. Okay, so we want the coordinates of the stationary points, and this is the information you've been given. So if we're talking about stationary points, we know that we need to find dy by dx. So we take each bit and we differentiate it first of all in terms of t. So there's dx by dt. Now y is product rule, and I'm being a little bit lazy and just writing my u and v below. Du equals 1 and dv is equal to negative 2e to the minus 2t. I then need to apply the product rule for dy by dt. And so I've got there u dv plus v du. And then I want dy by dx. I know that means I need dy by dt on the top. I'm taking the common factor out of e to the power minus 2t. You don't have to do that, but it does make things easier a bit later, and you'll see in a second why. So we've got dy by dx, pop it equal to 0. That means that the denominator is equal to 0, and so the factorising, I've sort of skipped having to factorise at that point. I know that e to the minus 2t can't be equal to 0, so I know that that bit's equal to 0. I get my value for t equals a half. So this is the point, that's the value for t, where I've got a stationary point. So when t equals a half, I plug it into the original equation for x and get a value for x. I plug it into the original equation for y and get a value for y. I could leave it as a half e to the minus 1. I'm just sort of tidying it up a bit, but that's fine. The first bit that I've written is fine. And so therefore the coordinate of the stationary point that I'm looking for is that 5 over 4 and then 1 over 2e. Okay, so that's the example for part A, but the others you can work on yourselves, and I will see you in part 2 to check those answers. The other thing that I'd like you to do is this, where you're using parametric differentiation. So you've got the parametric equations. The parameter this time is theta rather than t. Don't be freaked out by that. That's quite common when you've got angles to use theta. So you need to find a gradient function, dy by dx. You need to use that with that value of theta, and remember it's equation of a normal, not an equation of a tangent, so be careful. So please try that question too. And the final thing I'd like you to do when this video finishes is I'd like you to have a go at this exam question. You've got to find dy by dx, and you've got to find an equation of a tangent when t equals a particular value. Okay, so I will leave you there, and I will see you in part 2.